Now we will learn the main topic of this course, that is group. Group is the most basic algebraic structure. There are many algebraic structures like group, fields, rings, vector space, and so on. But group is the fundamental. And group is a set with binary operation and has some extra properties. So without further ado, let's start with the definition of group. Definition of the group. A non-empty set with binary operation, say star, is called a group if it satisfies the following properties. First property is closure property. Closure property is what? If AB belongs to S, then A star B belongs to S. Second property is associative, that is group operation must be associative, and associative is equivalent to this. Third property is group must have an identity element. We know that identity is unique, so there will be only one element which work as a identity, but it should have one identity. Existence of inverse. For all element of S, there should be a B such that B is inverse of A. And since the group operation is associative, we know that inverse is also unique. Now we will look at the remarks, some of important point to notice. And the first thing is that closure property is a redundancy. Means closure property is not necessarily here. Closure property is just saying that the given operation is a binary operation, nothing else. So basically, in the definition of group, there are only three requirements, and those are 2, 3, and 4. First thing is equivalent to saying that the set S with binary operation. Once you say that the operation is binary, you don't have to say that it has closure property. Both are actually same thing. So basically you omit this condition from the definition and you can take only 3. When operation has no ambiguity, we often omit the star and we directly write A star B as AB. This is a convention. Now powers are written as follows. Suppose you want to know what is A power n. We write A star A n times as powers of A to the power n. In the case of additive group, we know that A plus A n times again n times is written as na. Group is mainly classified into two types of group. One is called abelian group, others are called non-abelian group. A group is abelian if the given binary operation is commutative. And commutative, we already have learned about commutative binary operation, that for all AB belongs to Z, we have A star B equals to B star A. If you take any two element in G, they must commute. It happens sometimes that some element commute, but not all. Then we say that group is not abelian. Non-abelian groups are those groups which are not abelian. Now we will see some examples of group, and you must study lots and lots of example of groups because they are so fundamental in mathematics. They are everywhere. Whether you learn abstract algebra, real analysis, linear algebra, and many other paper, you will find many groups. So group is one of the basic algebraic structure, and you can find it anywhere in mathematics. The simplest example of group and most familiar to you is the set of integer with plus. And you can see that it has closure property because plus is binary operation on Z, or you can say that if you take any two integer, then their sum will be a integer. Plus is associative, we know that from childhood that plus is associative. Existence of identity, it has an identity 0. You can say that you can find the identity the way you have learned, that take E to be identity, then E plus M, where M is any integer, will be equal to M. Identity has no effect. So we cancel out M, we do the algebra as we have taught already or we have learned already, and E comes to be 0. Since 0 belongs to Z, it is the identity. So group has identity. Existence of inverse, if you take any M, suppose n is its inverse, then m plus n should be, and n plus m should be identity of the group, which is 0, and n turns out to be minus of n. Since for any integer minus m belongs to integer, so the inverse exists. In this way, we have shown that Z plus is a group. Also note that m plus n and n plus n are same basically. So the group is actually abelian. Z is not only uh, Z is integer is not only the set of numbers which form groups. Actually, the set of rational numbers, the set of real numbers, the set of complex number all form groups with plus. Not only that, if you take the set of rational number and remove the 0, it will form a group with respect to multiplication, because 0 does not has a inverse. We know that there is nothing like 1 by 0. Similarly, if you take r star, that is r minus 0, c star, set of complex number minus 0, also forms a group with multiplication. There is one more interesting group, is q plus. Q plus consists of only positive integers, and it forms a group with multiplication. Similarly, R plus forms a group with respect to multiplication. And note that Q plus with respect to multiplication is subset of Q star multiplication. So this is a group, and inside that this is another group. Okay, inside, and this set Q plus is subset of this. So we actually call it a subgroup. Group inside a bigger group are called subgroup of bigger group. After numbers, now see some other kinds of group. Consider the set S of the form of a plus root 2b, where ab belongs to rational number. My claim is this forms a group with respect to plus operation. So S is basically subset of real number. So if it is a group, it will be a subgroup of this real number, R plus, S plus. We start with closure property. Basically we want to show that plus is binary operation on S. So we simply take this and we add that. You can see that A and C are rational number, then A plus C will be a rational number. A and D is rational number, then A plus D will be a rational number. So whole thing belongs to S, because it is of the form of some element x, some rational number, plus root 2 times some rational number, so it belongs to S. Similarly, we can show that associative, and for that we need three elements from S. We will add first this two of this, and then we will add this, and in the next time we will add these two and then add this, and we can see that both the expression will be equal. Existence of identity. So consider E equal to E1 plus root 2 E2 belongs to Q is identity. So we have to solve this identity equation. A plus B root 2 plus E1 plus E2 root 2 equal to A plus B root 2. So basically we take some arbitrary element belongs to say X plus identity E must be equal to X. And after solving we will find that E1 equal to 0 and E2 will be also 0. And since 0 can be written as 0 plus root 2 times 0, this will belongs to S. Now the last part, we have to show that existence of inverse. Since we have got identity, you know that identity is required to define inverse. We have to check always that identity belongs to the set. Existence of inverse is impossible without existence of identity. Suppose you have one element a plus b root 2 and consider c plus d root 2 is its inverse, then their sum should be equal to identity. And it turns out to be, by solving the equation, c equal to minus a, d equal to minus b. If a plus root 2 b, inverse of this is actually minus of a plus root 2 b. Now we will look at a general example of groups. General examples mean it has many concrete examples. Let's see how. Let x be any set, so it depends on you. You can choose any x, so there will be a infinite number of such x is possible. So you can take any x And now Sx will be the set of all bijections from x onto x. You can say, so since this is a bijection, so we can write x onto x. So if you take the set of all functions from x to x where f is a bijection, then my claim is Sx form a group with respect to composition of function. The set Xx contains functions. So what should we expect in this set as a binary operation? Composition of function. We know if we compose two function, we always get a function. First thing we will look at closure property. That is, if we compose two bijection, we will get a bijection. Suppose you have two bijection on x, fg belongs to xx, that is fg are bijection. And how bijection is proved? If x1 not equal to x2, then its image are not equal. So x1 not equal to x2, hence fx1 not equal to fx2 because f is a bijection, and hence gfx1 is not equal to gfx2 because again g is a bijection. So f compose g of x1 is not equal to f compose g of x2, and thus f compose g is a 1 function. Also we need to show that f compose g is a onto function, and 1 and onto imply that f compose g will be a bijection. In order to show that f compose g is a surjection or onto, so we have to take any element in x and we have to show that its pre-image exists. So we start with the element here, and for all x belongs to x, there exists y belongs to s such that gy equals to x. Why? Because g is a bijection, so g is a surjection, so every element has a pre-image under g. So the pre-image of x is y. Again y belongs to this set x, and f is a bijection, so its pre-image exists. So pre-image of y is z, so f compose z equal to y. Now using both equation, this 1 and this 2, we will get that gy equal to x, and we will replace y with fz. So thus we will get f compose g equal to x, and thus pre-image of x is z. So f compose g is a surjection. In this way we have proved the closure property that if f is a bijection and g is a bijection, then f compose g is a bijection. Now we have to show the associative property, and for this we have to show that f compose g composed h equal to f compose g compose h. First we will you open this operation or evaluate this operation, then we will evaluate this operation, while on right hand side first we evaluate this operation and then we evaluate this operation. So how we will show that two functions say phi and psi are equal? Basically the way to show that two functions are equal is its effect on each element. So if fx equal to psi x for all x in domain, then we say that both the functions are equal. In order to show that both the functions are same, we will take any element belongs to S and apply this function on that. And for that we will first evaluate this binary operation, and this will be equal to this. We will consider this as a function, one function, and then we will start evaluating that function, and you can see that this is equal to this and this is equal to this, thus both the functions are same. Thus composition of function is associative. Now we will look at existence of identity. So we need one function in Sx or one bijection in fx Sx such that, let's say I be the that element, and I composed with f composed with I should be equal to f. So basically composing I has no effect on, and we already know that such function actually exists for all any set from x to x. Just take x and its image should be x. This function will act as a identity, and we can verify that I composed fx equal to f composed ix equal to fx, and this is true for all x. So ix, now this is equal to this, and this is equal to this, and this is equal to this, and this implies that this is ix is x, this is equal to, this is fx, and this is fx. So this is a identity, all three expressions are same. So this proves this equation or identity. In this way we have shown the identity, existence of identity. Lastly, we have to show the existence of inverse. It means that for any bijection from x to x, there exists a bijection from x to x such that f composed g equal to g composed f equal to identity. So let's define a by a rule or method which sends element from x to x such that whenever y maps to x, gy equal to x whenever fx equal to y. We need to show that g is a bijection. Okay, first we have to show that g is a bijection, and in order to show that g is a bijection, first we have to show that g is actually a function and it is called g is well defined. That is, we have to show that g is well defined. So in order to show that g is well defined, what we take two representation of same element and we apply g on that, and we will show that their images are the same. So suppose y1 is equal to y2, hence there exist x1 and x2 such that fx1 equal to fx2, and this will lead to x1 equal to x2 because f is 1 function. So if images are same, then their pre-image will be same, and hence gy1 equal to gy2. Each element has unique element. This proves that each element of x has unique element under g. So g is a well-defined function. Now we will show that g is bijective. In order to show that g is bijective, we have to show two things. First is g is 1 that is injective, and second g is onto. In order to show that g is 1 function, we take two distinct elements of set x. Suppose y1 is pre-image of x1 and y2 is pre-image of x2, then fx1 is y1 and fx2 equal to y2. So this is equal to this, and since f is 1 then x1 is not equal to x2, and hence gy1 is not equal to gy2. Thus g is a injective function. We have used the property that f is 1 to obtain x1 x2 from this fx1 not equal to fx2. Now for all x belongs to x, in the next part we will show that g is surjective. So what you have to do, you have to show that g from x to x, and if you take any x here, you will get a pre-image here y. So we have to translate this into f because we are proving anything about g using the property of f. Actually it means that f is a function from x to x. The question is asking to for all x y, and we know that f is a function, so every such x has a image, and since x has a image, it turns out to be that will be pre-image of x under g. Thus g is surjective, and by combining both g is injective and surjective, we can say that g is bijective. And from all these four properties, as we have shown earlier, we can say that Sx forms a group under composition. Another very important property about this group is that this group is non-abelian. Actually we know that composition of function is not commutative. You can take simple example to prove this, or later we will see that some examples, definitely some examples of some bijections, that bijections are not commutative. So Sx is a non-abelian group. Sx is a very general example of group, and if you take different sets, then Sx will be different. For example, take x to be 1 to 3, and then S3 is called the set of all bijection from x to x. This is denoted by 3. In general, if you take x equal to 1 to n, then Sx will be the set of all bijection from x to. Now S3 will be the set of all bijection from x to x, and you can see that there are 6 of them: phi 1, phi 2, phi 3, phi 4, phi 5 and phi 6. In order to understand the structure of this group, since this group is finite, it is always beneficial to make a operation table. You can see that phi 1 is working as identity because it is sending 1 to 1, 2 to 2, 3 to 3. So this will be the identity and it has no effect on any element. So the first row and first column of this table will be the same. In order to evaluate phi 2 composed with phi 2 by applying 1, 2 and 3. If you apply phi 2 composed with phi 2, you can see that phi 2 is phi 2 1 is phi 2 1 is 2, and again phi 2 2 is 1, so it will be 1. Also phi 2 2 is 1 and phi 2 1 is 2, so it will be 2, and phi 3 phi 2 applied on 3 will be 3, the last element, since these are bijection. And we can see that this is actually identity because it is sending 1 to 1, 2 to 2 and 3 to 3. So phi 2 composed with phi 2 is phi 1. Before going further, I will recommend you to pause the video and try to fill this table, complete this table.